All right, so as we continue on our notes here, you guys have the package out in front of you here, and we talked yesterday, or last day, I guess we did test last day. We talked about drawing stereoisomers, and we talked about enzymes and substrates. We talked about chirality, left and right-handedness. So as we pick up the notes here, I want to start talking about something called functional groups. So up till now, we've only looked at hydrocarbons where carbon atoms are linked only to carbon. Carbon atoms are linked only to carbon and other and hydrogen atoms. But carbon atoms can also form strong covalent bonds with other elements. In an organic molecule A, and now here's where you'll start to fill in your blanks in your notes in front of you there. Try and highlight your spaces for you. In an organic molecule, a functional group is an atom or group of atoms that always reacts in a certain way. So functional group is your first blank there. The addition of a functional group to a hydrocarbon structure always produces a substance with physical and chemical properties that differ from those of the parent hydrocarbon. Okay? So if you have a hydrocarbon and you have some other, so let's say we have carbon, okay, so what would this, what would this be, this molecule here? All single bonds between the carbons. We've got H's here. Anybody remember? So what's the name of this one? I heard an ethane, I heard a butane. Methane. Okay, I heard ethane, methane, and butane. So remember the number of carbons. Remember the little thing you need to remember. Meth starts with meth, then goes to what? Meth, eth, prop, and bute. Right? Meth, eth, prop, and bute. So had a bunch of different answers here. This is meth, eth. This is a single bond. So whoever said ethane was correct. Okay. All right, so maybe some of you need to review that. That's very important. You need to know that, okay? That's something we need to know at this point. So ethane, now if I did something like this, took away these hydrogens, and I put this here, and we have hydrogens here, 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 and here, what's that molecule? Meth. Okay, it's not meth because there's still two carbons, so it's ethene. Yeah, the double bond is the ene, okay? All right. So, yeah, okay. So we might have to review that, okay, in your notes. You guys need to study that. So what happens if we have, instead of just hydrogens and carbons, right, we have, something like this, okay? That's possible, and this would be a functional group, okay? Yeah, that's an alcohol group. We talked a little bit about that, didn't we? Yeah, that's right. So that's an alcohol group. This is a functional group, okay? An example of a functional group. So they have obviously different properties. They have different structures, and they'll have other atoms other than carbon and hydrogen in them. Okay? So this is ethanol. Yes, that is absolutely correct. Good job. Okay, so the symbols, the symbols R and R prime represent carbon chains or rings. Now this is something that you'll see in your textbook, in the notes, in organic chemistry. R is a symbol for carbon chains and rings. So if we have R and we have something like R prime, that just means that these two carbon chains or rings are different. Okay? They're not necessarily identical, but these are carbon chains or carbon rings. And so what we might have in explaining what an alcohol is, we might have something like this, ROH. And as a matter of fact, that is your typical designation for an alcohol group, molecule. So we have some kind of carbon chain or ring attached to an alcohol, an OH functional group. So this could be methanol or ethanol, okay? Could be butanol, could be hexanol, right? Could be cyclobutanol. So carbon chains or rings. All right, so it's just a side note. An asterisk here represents a hydrogen atom, carbon chain, or C ring. So if you have some kind of asterisk, it could represent any one of these three. But R is specific to carbon. All right, so let's take a look at our organic compound functional group chart. Okay, let's talk about some of the functional groups, and you have some blanks here to fill in as well. So a halocarbon, okay? So that word is split up into two parts, halo and carbon. And so a halo is short for halogen. So if you have some carbon group connected to a halogen, and in this case, in this chart, it's represented by an X. So our X is halogen with the X attached to some kind of carbon group there. An alcohol, as we've mentioned already, is ROH. Now, the functional group here is halogen on the first one. The functional group here is called a hydroxyl functional group. So the molecule itself would be an alcohol. The functional group only, the OH, is called a hydroxyl group. So you know how the ions, this is a hydroxide ion. Well, an O and an H bonded to a carbon chain or ring would be a hydroxyl group. Okay, so the third one is an ether compound, an ether. That's ETHER. And again, we're going to study these in detail. So this is just your first kind of look at what these are. So don't get too excited that, oh my goodness, I have to know all about these by tomorrow. No, we're going to be taking these kind of one section at a time. But an ether group has some kind of carbon chain or ring attached singly bonded to an O, which is in turn singly bonded to another carbon chain or ring. Okay, so you could have something like, just CO, C, whatever, with H's all around. Okay, just like that. No other bonds for the oxygen, and there's only two bonds here, so it has it has pairs of electrons that are unbonded. Okay, right? So that's called an ether, and an ether functional group would be this ether functional group right here, just the oxygen in there. All right, amine. Amine, a compound type, is a carbon chain or ring with an NH2 on it, an NH2. Okay. If you guys need to shut these lights off, that's fine. If it's too much glare in the back there, it's up to you. So amine, NH2, and it's an amino functional group. Aldehyde, okay, aldehyde is the next group, and it involves this functional group right here, which is called a carbonyl functional group, carbonyl. All right, so it looks like this. And remember, this asterisk here could be another H or it could be a carbon ring or chain. So you're looking for this C doubly bonded to O, singly bonded to H. That is called a carbonyl group. And the compound type is aldehyde. Okay, so this is a ketone here. And that has a carbon chain or ring on either end. And in the middle, we have the C doubly bonded to O. I should clarify that the carbonyl group is really just this. This is the carbonyl group here. Okay, just so you're not getting that confused. This is the carbonyl, C doubly bonded to O, because there'd be different things on here. And again, we'll go over this in detail as we move through. Just fill in your blanks here for now. So this one is a carboxylic acid. Carbo, XYLIC, carboxylic acid. So it has a carbonyl group and it has an OH, which that together is called a carboxyl group. And then just a couple more here. An ester, E-S-T-E-R, not E-S-T-H-E-R, like the Bible character, but ester, E-S-T-E-R. And that's going to have your carbonyl group here, and it's going to be attached to an O and then to a carbon chain. So C bonded to two O's here. That's the big thing, and that's an ester group. So, and finally, the amide group, different than the amine, but similar. The amide does have this C doubly bonded to O. That's pretty common in a lot of these, isn't it? And then it has an NH here. Just an N with one H, not an N with H2 like amine, but N with just one H. and then another carbon group. So that's just the chart. You'll refer back to this chart as we move through, but like I say, we're gonna separately sort of take a look at each compound type, what they look like, what their bonds are like, what they're used for, all that sort of stuff. We're gonna take a look at each one of these separately, okay? So this is just your chart to introduce you to the functional groups that we're going to be studying. Yep. Yeah. No, it's this that's highlighted here. The carbonyl group would be the C doubly bonded to O there. Yeah, and we'll talk more about that as we move through, for sure. It's the C doubly bonded to O is the important part. But let's take a look at the halocarbons here first in a little more detail. Halocarbons. So next page on your notes there. Halocarbons. All right, as we mentioned, the halo stands for halogens and obviously attached to a carbon, ring or chain. So it's pretty straightforward. Recall the elements in group 17 are fluorine, chlorine, bromine, iodine. Those are halogens. Halogens in group 17. And so the table looks something like this, right? And group 17 is this group right here. So these are the halogens. Any organic compound that contains a halogen substituent is called a halocarbon. So if we've got some kind of carbon ring or chain and we've got a halogen on it, you'll see here that there's many different words for different things, like substituent. Okay, that means there's something that's attached onto it. Is it a functional group? Yeah, technically it is. You'll see other words for a functional group like substituent as well, but it's called a halocarbon. If you replace any of the hydrogen atoms in an alkane, and remember alkane would be singly bonded carbon chains, with a halogen atom, you form something called an alkyl halide. Lots of different words you're going to be introduced to here. And organic chemistry is a lot of new terms and stuff. And we'll try and keep everything straight with our charts and your notes and things like that. Okay. So yes, this is a halocarbon. If you replace, though, an alkane specifically, because this is a group all into itself, it's got a special name, it's an alkyl halide. Okay. So a carbon ring or chain, I guess, that just has single bonds. So this is chloromethane right here, chloromethane. So you see the base is a methane. This is a methane group, except for one hydrogen has been replaced with halogen. And which halogen? It's chlorine, so you would have the prefix chloro. Chloromethane. Meth is the 1C. Chloromethane. All right. If you had something like this, what do you suppose this might be called? That's right. Fluoromethane. Fluoromethane. Very good. What about this? Where all these are H's here. What do you suppose you'd call this one? Sorry? Bromethane? Broethane? Okay. Yo, bro, ethane. It's my bro. Ethane's my bro. Yeah, so this is actually bromoethane. Yeah, you do. Yeah, broethane. Bromethane. So you do have to have the prefixes, the bromo, fluoro, chloro, and iodo. So you do have to have the O's in there for the halogens there. Yes, I'm serious. What's iodo? Really? Okay. So look at the halogens there. Which one do you think it would be?
Like, what is that connected?
Well, I've drawn this one and I've drawn this one. Those are just the prefixes for ones that would, haven't drawn yet. So this would be, if I put a Cl here, that would be this one, chloroethane. And if I put just an iodine here, that's iodoethane. Okay? That's all I'm saying. So if you had this ethane kind of root or base, and you put an iodine on it, it would be this iodoethane. Yeah. Acetine is not really, it's in the group, but acetine is not a usable compound really. So you'd never actually see one. Yeah, AT number 85. It's not really a usable halogen. It's barely even part of the group there, number 85. So, anyways, okay, good.
Yeah.
All right, naming halocarbons. We've already talked about this a little bit just now. But for alkyl halides, a prefix indicates which halogen is present. The prefixes are formed by changing the "-ine" part at the end of each halogen to O. So that's where you have your, as I mentioned, if you want to write this down, if you haven't yet, fluoro, chloro, bromo, and iodo. Astatine, I guess if you had to do it, following these rules, what would it be? Astato. Astato. But again, astatine is not really, I've never seen that actually as a compound that's used at all. Astatine is barely even a real compound. It's more theoretical than anything. So you don't have to worry about astato.
So just the first four, we never have to think about the other one?
That's right. So yeah, so don't worry about astatine. Like I say, it's only a product of nuclear disintegration, less than 30 grams on the whole Earth apparently. So don't worry about it. It's not going to be used for anything. All right, if more than one kind of halogen atom is present in the same molecule, the atoms are listed in alphabetical by name. Okay, so alphabetical order. The chain must also be numbered in a way, okay, now this is very important, numbered in a way that gives the lowest position number to the substituent that comes first in the alphabet. So the lowest position for the naming is the one that the element that is attached here that comes first in the alphabet. So we'll go over this for examples, but if you were to have a fluorine on a chain and a bromine on a chain, you would have to name the compound with the bromine first because it comes first alphabetically. And when you're naming the carbons, so when you're numbering the carbons when you name it, the lowest number carbon has to go with bromo because it's the first in the alphabet. That will become very clear in the next few minutes as we do some practice. So similarly, finally, the benzene ring in an, and now I don't know, did we talk about this? Oh yeah, aryl. We kind of glossed over this a bit. An aryl halide, this is from your last page there. An aryl halide is an organic compound containing a halogen atom bonded to a benzene ring or other ring aromatic group. Okay? So the alkyl halide is a carbon chain alkane. Aryl is a benzene ring or other aromatic kind of cyclic group. So we'll come across more examples like that too, but aryl halide is mentioned here. So similarly, the benzene ring in an aryl halide is numbered to give each substituent its lowest possible number. All right, so there are some examples in your notes. So let's talk about these here, and we'll take a look at them just one at a time. Actually, do I have my blanks? No. Okay, so let's take a look at them one at a time. So this one here, okay, is chloro because we have a Cl here, right? And it's attached to a benzene ring. So remember, this is a benzene ring with that circle inside there, showing those single double bonds, sort of hybrid bonding, the hybrid bonding there. So this is chlorobenzene. You name the prefix there, and then you name what it's bonded to, chlorobenzene. Okay, moving over to this one here. Okay, So these are two different ones here, listed right next to each other. So I'll put a little separation here. This first one, as we mentioned, we drew this one already. This is you might not have enough room in your notes there for them, that one blank. This is fluoroethane. Okay, there's only one halogen. And so naming is pretty easy. Fluoro, 2 carbons is eth, singly bonded ane. Okay, fluoroethane. Now this next one here is, now we have to name this, there's more than one halogen attached to this chain. So we have to start putting these things together. Okay. So fluorine is our only halogen. So that's the only little prefix we have to worry about. But we do have to state where these fluorines are attached, because this fluorine here could be attached over here at the end to the third one, or it could be attached to the second one. So we have one, naming this 1 carbon. This is number 1. 1, 2, because the second carbon also has a fluorine on it. We always put commas between numbers, and always put dashes between numbers and letters in this naming, okay? An important thing to remember as well. So this is 1, 2, dash. A funny little rule that we have to remember too in organic chemistry is, yes, we've named the 2 carbons. We also have to say that there are 2 fluorines. So you have to say difluoro if there's 2 fluorines. It's not enough to say 1, 2 fluoro. You have to say 1, 2 difluoro. Difluoro. We have 3 carbons in total. So meth, eth, prop. All right, so we have prop here. And then we have single bonds only between the carbons. So this is ane. Okay. So naming is now starting to get a little bit more complicated, as we have to account for the carbon numbers that these things are attached to. We also have to account for the types of substituents or functional groups here that we have, the substituents in this compound, and of course the naming of the number of carbons in the chain and the type of bonds. So that's where you get this from. Yeah. Question. The 1 and 2 represent the carbons that the fluorines are attached to, first and second. And you would never count them as 2, 3. Why? Because you want to have the lowest numbers possible. So you wouldn't count from this side and go, oh, it's a 2, 3 difluoro. No, you'd want to keep those numbers the lowest possible. So this is going to be 1, 2. And we'll do more examples. You'll see that, okay? All right, so let's go down to C down here. Okay. All right. So C. What do we have here? We have 1, 2, 3. We have 3 different halogens on here. So this one is called, now we have to name the one that shows up in the alphabet has to have kind of the lowest number attached, and we've got to name that one first. So that's bromine. So we have 1 dash bromo, because it's on what would be the first carbon. And then we have to number the carbons in order, going out from number 1. So this is going to be 1, 2, 3, 4. Those are the number of carbons. Between a letter and a number, we put a dash. So 1 dash bromo dash. What do you name next? Well, alphabetically, we have to name chlorine next. So this is 3 dash chloro. Notice that if there's more than one more than one halogen, we just do the prefix there. We don't actually, we actually wait till the end to put the butane part. So just the prefixes. And then finally, the last one is fluorine. And that's on the second carbon. So 2 fluoro. We've got all the halogens listed here now. So now you go ahead and you focus on what chain that they're on. This is meth, eth, prop, bute. It's bute. All the single atoms, single bonds there mean it's an ane. Okay? So that's how you name that. Yeah, question?
So, like, if
Mm-hmm. Remember, yeah, so the question is if bromine was in the middle, how would you name them? Well, you would give bromine, because it comes first, you would give it the lowest possible number. So you would name it from one end or the other where bromine has the lowest possible number.
Like one has to start.
So if it was like this, bromine, fluorine, chlorine, like that, okay? So if it was like this, then you would give bromine the number 2. This would be number 2. It would not be 3. So bromine would have to be 2. So this would be 2 bromo. What comes next in the alphabet? A, B, C. So then this would be 2. So this has to be 4 chloro, 1 fluorobutane. So you would give the one that shows up first in the alphabet the lowest possible number. So you wouldn't put a 3 here. It wouldn't be 1, 2, 3. From this end, it'd be 1, 2. And then everything else is whatever numbers that they get. Does that answer your question? Okay, good. All right, anybody else? All right, let's take a look at these two then. These are two different ones as well. So kind of make a cut line here. The first one, easy, fluorobenzene. And this one here will take a little bit of thinking as well. So we have a benzene. We do have to remember that at each corner, even though it's not listed, these are all carbons. Okay, those are all carbons. Now, which one comes first in the alphabet between bromine and iodine? Well, bromine comes first. So we have to write bromine first, and we have to give it the smallest possible number. If we're talking about a ring, we can start at any carbon and name it number 1. So the one that the bromine's on is automatically going to be number 1. That's going to be carbon 1. So I'm going to state it as 1 bromo. Okay. Now you have to decide which way you're going to count around the ring. And because iodine is on, like the two substituents here are both iodine, those both come next in the alphabet, and they're both the same distance away from the bromine, so it doesn't matter which way you go here. This is going to be a 1, and then if you go down here, this is going to be 3. If you go this way, that's going to be a 3, so it doesn't really matter. So we would name it as 1 bromo dash 3, 5, because there's 2 iodines. So 3, 5 dash. How many were there? Well, there were 2. So I need to put di. They're iodines, so that prefix is iodo. And then what is the parent, sort of the root molecule, the base molecule? Well, it's a benzene molecule. It's not an ethane or ethene or ethine or hex, whatever. It's benzene. Okay? Question, yeah? Bromo is not also attached to 3. This is iodo here. Okay, so 1 bromo, because bromine is the first one in the alphabet, it has to be named first, and it has to have the lowest possible number. Because it's a ring, I can start anywhere. This could be carbon 1, this could be carbon 2, 3, and so on. You can start anywhere. So to give it the lowest number, you would start here at 1. So 1 bromo. And then the 3, 5 is because we have 1, 2, 3, 4, 5, 6. We have an iodine on 3 and an iodine on 5. So why is the 3 listed first? Just because it's the lower number. Yeah. Is your question, why couldn't you do this 5, 3? Sort of, yeah. So you'd go with the lower number if you had to, like that. List the lower number first. Yeah.
I have a question for this ring. If you had both.
Okay, so more practice. Why don't we do something like this? Okay, how would we name this? So the first thing you want to look at is what kind of halogens do you have here? So this is obviously a halocarbon, right? It's an alkyl halide. we've got bromine here. That's one's going to come first in the alphabet. So I'm going to want to name that first. I'm also going to want to name, give bromine the smallest number for the carbon, if I can. So it's an obvious choice to make this number 1, and then this is going to be 2, 3, 4, 5. Okay? So we're going to give bromine a number 1, no problem. So 1. Now, what about the second bromine? Well, 1, 4 is what you got to do. Comma between numbers. Dash. How many bromines do we have in total that we listed here? 2, so that's a di. And what's the prefix for bromine? Bromo. Okay? So the 1,4-dibromo gives you the carbons, the carbon numbers, the positions there where the bromines are attached to, and you also tell me which halogen you have, bromo, dibromo. Okay? So then we move on to the, which one comes next, F or I in the alphabet? Yeah, F. F comes next. So then we go between letter and number, it's a dash. 2, right? Now dash your comma or what? 2 dash fluoro, because that's the fluorine is on the second one. There's only one fluorine, so I don't have to do di. I only have to list one number because it's only on one carbon. All right. Then I got to take, so this is taken care of now. I got to take care of this iodine. So it's on carbon number 5, right? 5. Iodo. There's only one, so you don't need a di or a tri or anything. Iodo. And what is this? 1, 2, 3, 4, 5. Pent. Ane, single bonds. Okay, so that's that's how you name that one. Any questions? All right, next page is your some practice there for you. So let's see here. Oh, before I give you all the answers there, go ahead and give those a try. Name those 3 on your next page of notes there. Okay, so take a, you guys have you guys got all those names? Got your guesses? I'll reveal the answers here in a second. I did highlight some things for you, give you some hints here on naming. It's maybe a little bit messy there. This one, I'll explain this in a second. But, so the first one here, okay, so we have, anybody want to shout out their guess? Do you think they're right?
2, 4.
Okay, it's 2, 4 I heard. This is going to be, it should be a 2, 3. Yeah, because that's the second one, third one. So you were close. All right, let's move the highly sophisticated blockers away there. This is all I can do on this program. So we've got 2, 3 dash difluorobutane. 2, 3 difluorobutane. So yeah, so we want to count those carbons. Okay, so I gave you a little hint here on which carbon should be number 1, again, because we've got bromine as the first in the alphabet. So we should start naming our carbons from the right side. Oopsie. Come on. All right. So this is going to be 1. Oh, this is not as smooth as I had hoped. There we go. Okay. So the top one here, number 2, would be 1 bromo, 5 fluoro, and because there's 5 carbons in total, chloropentane. So 1 bromo, 5 chloropentane. All right, for number 3, you want to start with the bromo, because it comes first in the alphabet. And so you want to make either one of these number 1. Doesn't really matter which one. Okay? If you make this 1, then you would probably make this 2 instead of going around the chain naming them this way, because you want the bromines to have the smallest numbers possible. So this is going to be 1, and 3. So it'll be 1,3-dibromo, 2-chlorobenzene. 1,3-dibromo, 2-chlorobenzene. Okay, any questions about those? Yes, no? Okay. All right, let's talk about properties of halocarbons. What are the properties? What are they like? Well, you can imagine, probably you're thinking about halogens. They have a high electronegativity, right? They like to form bonds. The halogens themselves are, form 1 negative ions. They have a high electron affinity. So what kind of properties would those produce in organic molecules? The boiling point and densities of alkyl chlorides are higher than the alkene with the same number of carbon atoms. So when you put a chloride on a carbon chain, then it increases the boiling point and the density. The boiling points and densities also increase as the halogens get larger. So let's think about that for a second. Boiling point. Okay, so the amount of energy it takes to break apart or to split apart the molecules in the liquid stage to put them into the gas stage. So there's a little bit of a higher attraction, okay, a little bit of a higher attraction between an alkyl halide than just the straight chain carbon. I suppose that the chlorine or the bromine or the fluorine would have a big influence on the intermolecular forces, right? You've got this, first of all, you've got this huge molecule or huge atom, way bigger than hydrogen and bigger than carbon. And in some cases, like chlorine, bromine, right? Many, many times bigger. And you've got how they draw the electrons to themselves, right? High electronegativities. So instead of having, let's say, carbon chains like this, where the electrons are sort of, equally spread out, you have something like this, right? You have a chlorine, oops, yeah, I'll just do Cl, where you have this huge collection of electrons here maybe, and it's smaller over here, right? And so this is a partially negative end, so this becomes polar, right? And this is partially positive. And so there's a little bit more attraction in between the molecules, which makes it harder for them to separate. So we need to apply more energy to separate the molecules. Now, the densities as well. You can imagine if this is a large atom here, and these are smaller ones, and the hydrogens are even smaller, then the density of the actual material in the same volume might be higher as well. So we're stuffing in largely electronegative atoms and much larger atoms as well. So that would change the boiling point and would change the density. Boiling point and density. And also the increases as halogens get larger. So what else? Why else would this be explained? This occurs because the halogens get larger, they have an increasing number of electrons lying farther from the nucleus. These electrons shift position easily, so the halogen substituted hydrocarbons have an increasing tendency to form dipoles. So the dipoles are those partially positive and negative ends. Because dipoles attract each other, this takes more energy to separate them. So that was the explanation for the boiling point there. Okay, any questions about this page here? Okay, you may be dismissed. All right, in the next video, we'll finish off halocarbons, uses of halocarbons. We'll also get some practice in naming and drawing halocarbons. Next video.